Hey everyone, I'm Chris.
I'm Steve.
I'm Brenden.
And today we're going to be telling you about our model, which is a footing drainage system. So, what exactly is a footing drainage system? So, usually they're placed at the foundation of a home and they're used to move rainwater away to prevent flooding and any damage to the home. And the purpose of this project is to analyze why changing the diameter of a footing drain can yield to less flooding in the home and less damage, because flooding can lead to rot, rust, mold, and a lot of problems. So how do we analyze this system? So we're going to be analyzing a dual tank system to simulate a septic tank and sewer networks, and we're going to determine how long it's going to take for the system to reach a steady state. So our outline of this experiment, so like I said, it's a dual tank system with two initial heights, and we're going to be feeding a hose into the secondary bucket, and that bucket will have an outlet diameter of 3/4 of an inch. These buckets were connected together and all tubing was modeled as a resistance. Now we have some initial values. We have the hose length, pressure, flow rate, those initial heights, the dimensions of the pipe, and so on. And here we have a video. So as you can see, a large initial height, and as we move out throughout the time, you can see around 1:40 seconds we do reach a steady state in both buckets, so the level is not changing.
Okay, so this is the model of our system, a schematic of our two-tank system. The flow rate was determined by filling a bucket with a known volume and timing how long it took. We then figured out the equations of motion, which are on the second slide. We used the conservation of mass, where the height in each bucket, the rate of change of the height of each bucket was related to the mass flow into and out of the bucket. Once we had those equations, we could then calculate the transfer function. So we started with we took the dynamics equation for one bucket, solved one parameter in terms of the other, in this case H2 in terms of H1. We then substituted that into the second dynamics equation. Combined all our like terms, took a little pause of that, and then arranged that into the desired transfer function form. In this case, H1 of S over Q2 in of S. We then used that in MATLAB to run simulations. The first thing we did was the step response. You can see this graph is what happens when you just turn on the water without there being any initial conditions. In other words, the bucket started empty, you turn on the water, and this is the response that you get. The height stabilizes at around 0.1 meters. We then did the initial condition response, or the free response of the system, starting with 11 inches of water roughly in each bucket. The overall response of the system is then just a linear combination of those two responses.
By looking at the results of the simulation and the experiment, you can see that the time it takes to reach steady state was very similar, and it only took about 1:48 seconds to 2 minutes to reach steady state. The final height of the tank, you can see, was also very, very close to each other, one being 4.25 inches and the other one being 4.1 inches. And then from the last slide, you can see that as you vary the outlet diameter of the secondary tank, that there's a linear relationship with the increase in the diameter and the time that it takes to reach steady state. So the outcome would be even a slight increase in the footing of the pipe diameter would prevent flooding and increase the time it takes to reach the steady state value.
Thank you. And if anyone has any other questions or wants to know more, just feel free to contact any of us. Thank you.